1C. Sounds good. I can do that. But that means we got to do part B first because it says interpret. Oh, we got to do part A also. But yeah, I can do number 1. Before we get deep into doing this, I do want to make you guys aware I just found a couple minor mistakes on the answer key. I found them during 5th period. And then there is one that is a larger mistake. The one where there is a larger mistake is problem number 17, part C. And I will be fixing this after school and uploading it. So by like 4:30, it will be corrected. But number 17, part C, my answer on the answer key should be doubled. It should be times by 2. So my answer on the answer key should be times by 2. After 4:30 today, it will be corrected, and you will notice a difference there. You'll also be able to see the times 2 in the actual work when I correct it. All right, number 1. What is the probability that a randomly chosen household has at least 2 televisions? How do we do this if you have to do it by hand? Yes. Yes, times 0.37 all the way across the table. 2 times 0.20 plus 3 times 0.11 plus 4 times 0.05 plus 5 times 0.03. Sorry, that's the expected value. That's part B. I wrote it in the wrong section. That's my expected value. So expected value is the same thing as the mean. And so when you multiply all of those together and you add it up, you get 1.45. Since I was writing this in the spot for part A, how would you do the part A? Yep. We're going to add 2 through 5 together. So 0.20 plus 0.11 plus 0.05, forgot my plus sign, plus 0.03, and you end up getting, yep, 0.39. So choice D. All right. For part B, finding the standard deviation, there is a way to do it by hand. We didn't do it by hand in class. I'm not going to ask you to do it by hand on the test. This is where I would put things into lists. So list 1, list 2. Thank you. And then you would go to stat, calc, 1 variable stats, and you have to make sure that you put L1 and L2 in when you do the 1 variable stats. When you're working with the yellow calculators from the back of the room, it will prompt you, what do you want for X? What do you want for frequency of X? And when you pop all of that into the lists, and then you do stat, calc, 1 variable stats, you should get 1.268 approximately. All right. So far, so good? All right. Interpreting both of these. Let's interpret the mean of X first. What is X? Like, what does X mean here? Number of televisions. And the mean would be the average number of televisions. So the average number of TVs in a household because we're not talking about the average number of TVs in the state or the average number of TVs in a school building. We're talking about the average number of TVs in a household after the long run. So after sampling many households, is about what? Yes, is about 1.45 TVs. So yesterday when we were going through the free response questions and we were looking at the interpretations of the mean, the interpretation of the mean, they always wanted you to have at least 2 of the 3. They want context, so they would want to see something about televisions in there. They would want to see something about average and something about the long run or this being repeated many times. Yes, sir.
This might be a dumb question, but why do you put after the long run and many times? So can't you just put like 1 and
So that's a really good question. The reason that I have both of those there is that this isn't the average after just doing one collection of many households. Like if I select 100 households, I would say that's many households, right? If I collect 100 households and I add up all the TVs and divide by 100, I have the average for that group. Might not come out to be 1.45. But if I were to repeat that study again, I pick another group of 100 households and I calculate the average. And then I pick another group of 100 households and I calculate the average. If I take all of those and look at the average of those averages, that'd be 1.45. So that's the idea that I'm getting at here, is that if you select a lot and find the average, select a lot and find the average, select a lot and find the average, and then we average all of those. So in the long run, when we do this over and over and over, or another way to think about that is if I keep adding more households to my sample, the more and more households that I add, the closer and closer the average for my group is going to get to 1.45. Does that help a little bit?
Yeah.
Okay. One of the biggest reasons why I added that in is because we were missing some of that language there and ending up with partially correct instead of essentially correct on those questions. All right, interpreting the standard deviation now. The number of TVs in a household typically varies by about 1.268 TVs from the mean of 1.45 TVs. Standard deviation tells us about variability. So on either side of 1.45, about 1.2, 1.3. So I would expect anywhere, like I wouldn't be surprised if somebody had a number of TVs anywhere between like 0 and 3. The average is 1.45, going down and up from there. We're sitting about 1 to 3 TVs is what would be typically found. What else would you guys like to talk about? Yes. Number 2? Absolutely, we can do number 2. A random variable x has a probability distribution as follows, and I see something in this probability distribution that we haven't seen before. K. K is just a variable. We know that a probability distribution has probabilities that all add up to what? 1. So if I add all of these, it should add up to 1. Since k is just a variable, I can combine like terms together. What do you get if you add 2 plus 3 plus 13 plus 2? So we have 20k equals 1. Divide both sides by 20. What is 1 over 20? How much? 0.05. So if k is 0.05, then 2k would be what? 0.1. And 3k would be 0.15. 13k would be 0.65, and then we have another 2k, so another 0.1. How could we verify that we did this right? Add them all up, and it should add to 1. So that's really what our probability distribution looks like. The probability distribution has x and p of x. Probability of 0 is 0.1. The probability of 1 is 0.15. The probability of 2 is 0.65. And the probability of 3 is 0.1. I don't know what this is a random variable for, but there's only 4 possible outcomes. For everybody that would be involved in this survey, it's either 0, 1, 2, or 3. The probability that x is less than 2, if x is strictly less than 2, it could be what? It could be 1 or 0. So what's the probability that it's a 1 or a 0? 0.25. Did that answer your question? A question like this, and the whole reason why it has the K's in there, what they're getting after with a question like this is, do you understand that a probability distribution, that all those probabilities have to add up to 1? Can you use that fact to work backwards here? All right, what other questions did we have? Yes. 11, absolutely. Jen's commute to work requires that she take the blue line subway, then transfer to the red line. The length of the trip on the blue line has a mean of 18 minutes with a standard deviation of 2 minutes. The red line trip takes 12 minutes with a standard deviation of 1 minute. So this is the average for the red line. If it wasn't an average, there would be no standard deviation. If it took 12 minutes and exactly 12 minutes without any difference every single time, the standard deviation, the amount that it deviates by, would be 0. So they're telling me the mean, the average there with that 12 minutes. And because she doesn't show up, get off the blue line, and get right onto the red line, she has waiting time between when she gets off the blue line and her red line train arrives. And it has a mean of 10 minutes and a standard deviation of 5 minutes. Assume, perhaps unrealistically, that these times are independent random variables. They just told me that they are random variables. We have 3 random variables here. We have the blue line, we have the red line, and we have the wait time. That's what our 3 random variables are. What are the mean and standard deviation of her entire commute? So the commute has to put all of these together. First, she rides on the blue line. Then she waits. Then she gets on the red line. So we are combining 3 random variables here, and we're combining them by adding, because these times just accrue, they add on to each other. To find the mean for the commute, so we're going to do the mean of, I'm going to call this random variable C. When we combine random variables together, what do we do with their means? In this case, we're going to add them. So we're going to take the mean for the blue line plus the mean of the wait time plus the mean for the red line. So we have 18 plus 10 plus 12. And what does that give us? 40. So she has an average of a 40-minute commute time, which means I can throw out options D and E. They did not take that wait time into account. Standard deviation is a little bit trickier. I can add means. Can I add standard deviations? No. When you are combining random variables, you take the variability of the first one, and that combines with the variability of the second one. Whether you're adding or subtracting these random variables, putting them together always makes it more variable. I can't add the standard deviations, but I can add what? I can add the variances. So if I want the standard deviation of the commute time, I need to do the square root of the standard deviation of the blue line squared, because that's the variance, plus the standard deviation of the wait time squared, plus the standard deviation of the red line squared. So that would give me the square root of 2 squared plus 5 squared plus 1 squared. Two squared is 4, 5 squared is 25, 1 squared is 1. So I'm going to add 4, 25, and 1 together, and we get what? Square root of 30. Square root of 30 is about how big? It's about 5.48. So this would be option B. Bless you. What would you guys like to look at next? Yes. 5B? Absolutely. Let's do 5A at the same time while we're here. It says, let the random variable X represent the weight of male black bears before they begin hibernation. Technically, they don't begin hibernation. They go into torpor. But I'm not going to get picky. They used to think they hibernated, but it turns out it's something different. Hibernation is a real thing, but bears don't do it. Yeah, they go into what's called torpor. Because they can come up out of it. Like true hibernation, it's like a biological clock and you can't wake up from it. Torpor, if the situation gets really bad, their body will come back up to speed and they can move around during that time that they're normally dormant. Right. Research has shown that X is approximately normally distributed. When you see approximately normally distributed, what should you do? Make a picture. Draw a picture for me. So we have an approximately normal distribution. What things do I put inside the parentheses next to the end? Mean and standard deviation. What's our mean here? 250. Standard deviation? 50. Make sure you label both of those. Mean and standard deviation. That's because there are different conventions for this, depending on the textbook you're using. My college textbook used a different convention here, so you need to label that so that the person reading it knows exactly what you mean by those numbers. Mean goes right down the center. So I have 250 here. There's something else that my picture still needs. Shading. And I have to have a boundary line for my shading, right? Where should my boundary line go? 325. Which side of the mean would that be on? Going to be on the right-hand side. 325. And which way do I shade this guy? Shade it to the right because it's a greater than. We shade to the right because it is a greater than. All right, so I have my beautiful, lovely picture. How do I actually calculate this probability? Normal CDF. So the probability that x is greater than 325 is equal to normal CDF and then what kinds of things do we have to feed normal CDF? Lower bound, what's our lower bound? 325. Upper bound. What's our upper boundary? Stupidly large, 1,000,000. Technically, my upper boundary is infinity, but I can't put infinity into the calculator. So that's why we pick something stupid big. What else do we feed this? Mean and standard deviation. So 250 and 50. And then I pop this into the calculator. So the probability that x is greater than 325 comes out to be about what? We're on number 5. Yes. Sorry, let me get to the right page here. There we go. 0.668. 0.0668. Best advice I have seen in the groups that I'm in with AP Stats teachers that have been doing this longer than, well, some of them longer than I've been alive. What they recommend is 3 significant figures. So even though I've taken this out 4 decimal places, I have 3 significant values. Especially important if numbers are very, very small. You still need to write down those leading zeros, but those leading zeros don't tell us much. It's the information at the end that we would need. All right, so this 0.668, that is what we have shaded right here. This shading is 0.0668 of the area, which is the same thing as the probability here, because the area underneath a distribution is always what? It's always 1, so that when we calculate the area, we're calculating the percent, the probability. For part B, they told us the probability. This is the area under the curve that needs to be shaded. Still 250 right down the middle. 250 and 50 next to my n. I know that I need 0.42 of the area shaded. Do I shade to the right or to the left? To the left, why? It says less than right here. So I want 42% of the area. That's less than half, right? So it's going to be smaller than where my mean line is. I don't know what this value is. But I do know what the area is here. This is 0.42. So far, so good? So basically, we start with the answer that we had in the last problem, or the type of information that would be the answer. And we're trying to work backwards to figure out what the weight is. So I need to undo the process that I had up above. What do we call operations that undo each other? Inverses. So instead of using normal CDF, we are going to use inverse normal. If you do second and vars, it's option number 3 for the inverse. This is what you do when it gives you the probability, when it gives you the area, and we want to work backwards. We need the inverse. Inverse norm eats 3 pieces. We have to feed it 3 things. What's one thing that we have to feed it? The area. That's the very first thing. So 0.42 first. And the mean and the standard deviation, yes. Now on these yellow calculators, it has an option at the end that says left, right, or center. That has to do with which way your shading is, which way your inequality is. There are a lot of calculators that get used on the AP exam that don't give you that option. So it's understood that we're going to go with the left. And I would just leave it that way. If we ever want to calculate an X value for a probability that's a greater than, we would just do 1 minus and do it the other way around. All right. So what do you get when you do inverse norm of 0.42 to 50/50? 239.91. Should we put units with that? Pounds. Remember, we just found the weight of a bear. 239.91 pounds. That doesn't feel very big for a bear. I'm just saying. Yes. Number 17, absolutely. This is the one that I told you part C has a mistake on my answer key. So you guys are going to get the right answer. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal. So if we're after a probability, we're going to have to draw a picture here. With a mean of 266 days and a standard deviation of 16 days. Choose 2 pregnancies independently at random. Do you guys remember when we were talking about the commute? We looked at the blue line, the wait time, and the red line. This is very similar to that. Instead of looking at randomly selecting one of the trains that runs on the blue line, randomly selecting one of the trains that runs on the red line, in this case, we're randomly selecting one pregnant person from a population and then independently randomly selecting another pregnant person from this population. So I have P1 and P2. These are both random variables. And they are distributed the same way. They're both normally distributed. They have the same means. They have the same standard deviation. Does that mean that these 2 pregnant people will have their babies at the exact same time? No. It means that the probabilities that they have their baby early or right on time or late is the same for these 2 people. What is the expected? When you see expected, what do you think? Mean. What is the expected difference? Difference means to do what? Subtract. Can we subtract the means of random variables? Yes. We can add the means of random variables like we did for the blue line, red line, and wait time. We can subtract the means of random variables. So the mean of the difference would be equal to the mean for pregnancy 1 minus the mean for pregnancy 2. What is the mean for pregnancy 1? 266 minus the mean for pregnancy 2, which is also 266. So what is the expected difference? 0. What is the standard deviation of the difference in the lengths of the two pregnancies? When we combine random variables, whether it is by adding them or subtracting them, things always become more variable. If it becomes more variable, I can't subtract those standard deviations. We can never subtract standard deviations anyway. But we're not going to be subtracting pieces because that would say that it's becoming less and less variable. That these pregnancies, when I look at two separate people, the chances that they have their babies close to 266 days is going to get closer together instead of farther apart. When I look at lots of different people, now things start to get more and more variable when I'm looking at, well, when is your baby born? When is your baby born? When is your baby born? So what we do here is the same thing as when we were looking at the blue line, red line wait time. We're going to add the variances together. This is one that gets missed all the time because it doesn't feel intuitive. So the standard deviation for the difference is equal to the square root of the standard deviation for pregnancy 1 squared plus the standard deviation for pregnancy 2 squared. So we have the square root of 16 squared plus 16 squared. What do we get when we do the square root of 16 squared plus 16 squared? You said 22 point what? 627. Okay, so for parts A and B, they didn't ask me about any probabilities. They asked me about mean and standard deviation. But down in part C, it says find the probability. Draw a picture. All right, so there's my normal distribution. It is normally distributed. This is for the difference in the lengths of the two pregnancies. So what is my standard deviation for the difference? 0. So right down the center of this, we have 0. And the standard deviation is 22.267. Don't forget to label both of those. I want to know the probability that the difference in the lengths of these two pregnancies is greater than 25 days. And this is where I made my mistake on my answer key. I wasn't totally wrong, but I missed something. If person 1's pregnancy is longer than person 2, and I subtract the lengths of their pregnancies, I would end up with what type of number? Positive number. If person 1 goes longer than person 2, if their number is bigger, then it's a positive. So I want to know if this is more than 25, but what if person 1 has the shorter pregnancy than person 2? then it'd be a negative. I have to consider this because this would still be a difference of more than 25. It's just where person 2 had the longer pregnancy than person 1. Normal distributions are symmetric, right? And I have the same distance away from the mean on either side here. I can calculate the probability of just one of these sides and then double it to get the total probability of everything that I have shaded in here. So we're going to do a normal CDF. So we are finding the probability that X is greater than 25 or X is less than negative 25. Bring that up here. So we do normal CDF. Let's do the right-hand side. So I'm going to use 25 as my lower boundary. Something stupidly large for my upper boundary, like 1,000,000. If somebody had a 1,000,000-day pregnancy, like that's... Do you get why we're picking something stupidly large? Like there is no pregnancy that would go out that long, so I'm guaranteed to grab every single one that is more than 25-day difference. And then mean and standard deviation. (22.267), and then I have to times this by 2 so that I get both sides. Label my mean and my standard deviation. When I do just this part right here, I get about 0.1346. But then I have to times that by 2 so that I get the other tail as well. So we end up with a probability of about 2,692. Yes. 627 instead of 267. I switched my numbers around. Thank you. 627. Thank you for catching that. I transposed my numbers. According to this, should we be surprised if 2 women have their babies more than 25 days apart from each other? If they were due on the exact same day, should it be surprising if they're more than 25 days apart? No. At what point should we be surprised? 5% or less. For a question like this, if they were to ask one of those like, should you be suspicious or this or that, or there's other questions like that, if this had come back to be less than 5%, then what we'd be looking at is a situation where the due dates were probably not calculated correctly. Because if they were due on the same day, and the difference between theirs occurs less than 5% of the time, then something went wrong earlier. All right. We've got 5 minutes. I have time for a short one. Yes. Let's go look at number 10. Which of the following is a true statement? The binomial setting requires that there are only 2 possible outcomes for each trial, while the geometric setting permits more than 2 outcomes. Is that true? No, geometric does not get more than 2. Has to have exactly 2. It's still binary. A geometric random variable takes on integer values from 0 to n. No. If x is a geometric random variable and the probability of success is 0.85, then the probability distribution of x will be skewed left, since 0.85 is closer to 1 than 0. Geometric random variables are always skewed which way? Always skewed right. It does not matter what the probability of success is, it is always skewed right. An important difference between binomial and geometric random variables is that there's a fixed number of trials in a binomial setting, and the number of trials varies in a geometric setting. Yes, that is true. The distribution of every binomial random variable is skewed right? Not necessarily. If it had said geometric, then that one would be correct also. Answer key is posted. We fixed the one that was majorly wrong. The other things that are wrong is like there's an or equal to and there shouldn't be an or equal to. And then there was a problem, not with the answer, but with what I wrote on problem number 9 on the answer key. What I said I fed into the binomial CDF. My X value is incorrect, but everything else about that problem, including the answer, is correct. So I'll go in there and fix those things. That'll be up before 4:30 today. If you have any questions while you are going through the test review or anything on AP Classroom or any of the multiple choice questions that have been assigned, please let me know. Send me a message in Canvas and I will get back to you. Yes.